Hey there, today we're going to do section 6.1 and 6.2. So let's open 6.1. Okay, let me start at the beginning. Okay, rational numbers and proportional reasoning. So rational numbers, that's another name for fractions, essentially. So a number that can be expressed as A over B. And we're talking about equal fractions, equivalent fractions, the simplest forms of fractions, ordering them to the denseness. So very basic terms, hopefully you know these, numerator and denominator. The numerator is the top number and the denominator is the bottom, or you can think about them as the dividend and the divisor. So this is an example for when you use them, like when you're solving equations, when you're trying to figure out the ratio of things or probability. These are ways you might describe them to a student. So this is like 1 out of 3 is shaded here. The number line model, you see 2 out of 3. And then here you see 3 out of different ways to illustrate fractions. To understand the meaning of any fraction, where B is an element of W and B is not 0, you can talk about parts to a whole. The whole is the question, the number of B of equal sized parts into which the whole has been divided. The number of A of parts, the whole that are selected. So like in this situation, what's the total number of parts? 5. And then how many are selected? 3. So that's what that was, all that was saying. And then proper fraction versus an improper fraction. So a proper fraction is just that the numerator is bigger than the denominator. And an improper fraction is that you have more pieces than total parts. So basically it's greater than 1. The top is bigger than the bottom. Here are numbers represented on a number line that are fractions. Equivalent fractions. So the idea of equivalent fractions is if you multiply the top and the bottom by the same number, or divide, depending on which way we're going, you get equivalent fractions. So if I multiply this by 2 and this by 2, I get 2/6. If I multiply this by 2 and this by 2, I get 4/12. So all of these are equal. And this illustration helps show that. Another way to talk about fractions is fraction strips, which I think are really helpful. If you just take like a strip of paper and you fold it in half, you can easily show that you have 1 out of 2 pieces. That's what the fraction means. And then if you fold it in half again and half again, then you can go up to fourths and eighths, etc. Or in this case, they divide it into thirds, so they get 1/6, and then they divide the 1/6 into halves. So they got 1/12. This is a fundamental law of fractions. Basically, you can multiply the top and the bottom by the same number, and that will be equal. So how would you solve this? One way to solve it is to figure out what you multiply by. So how did I get from 42 to 210? And the answer is we multiplied by 5. So that means we're going to multiply by 5 here. That's only one way to solve it. Honestly, if I was teaching this to students in an algebra course, I probably would not teach it like that. I would teach to cross multiply like this. 210 times 12 equals 42 times x, and then you divide by 42, and then at the end of the day, you're going to get 60. Side note, I like to teach students to not to worry about multiplying these big numbers together and to look for common factors. So I know since this is even, it has to be divisible by what? Hopefully you're saying 2. Right? So I'm going to divide this by 2, which means it's going to be 21. I'm also going to divide this by 2 because I have to do the same thing on the top and the bottom. So I get 6. Now, I know that this guy, 21, and 210, those are related, right? I know if I take 21 and multiply it by 10, I would get 210. So basically divide by 21, or take 210 divided by 21, and you get 10. And so what do I have left on top? 10 times 6, which is 60. So that's just another way of solving that problem, reducing by factors. It's in simplest forms if the GCD is 1. Now this is simplifying in terms of exponents. So again, they're writing out all the like factors. I don't always write whether equal to like that, but more so just divide. So I'm like, okay, 28 is even, 42 is even, divide by 2. So that puts it at 14. Divide this by 2, that would put it at 21. And then, let's see. Divide by 7, that makes this 2. Divide by 7, that makes this 3. A over a squared, b squared over b squared is 1. So I have 2 over 3a. This guy, a plus b squared, is like a plus b times a plus b. And notice that both of these have a factor of 3. So you can pull the 3 out front. And then one of these a plus b's is going to divide to be 1. So that's how you're left with the a plus b over 3. And this, we notice the common factor here is x. Also, just side note, never, ever, ever cross out part of a fraction like this. I just want to make sure you guys know that this is a grouping symbol. So this guy right here means that you have to do this together and you keep this together. The only things you can cross out is if you've pulled out a factor, then you're allowed to cross it out. So in this situation, I pulled out the factor, so now I have multiplication here and division. So now I can cross it out and say x plus 1 divided by x plus 1 is 1. And some students prefer to see it kind of like this. I could write this like this, right? I can imagine this is 1 times x plus 1. So I have x times x plus 1 over 1 times x plus 1. And what's x plus 1 divided by x plus 1? 1, because anything over itself is 1. And so anyways, that's how that part cancels, and we get x left. This cannot be simplified. Why can it not be simplified? Well, there's no common factor here. And like I said, you cannot cross out part of a heart, okay? Then the same idea here. Again, you cannot cross out this guy, but you can look for like factors. So I see that these both have a 3. So first you're going to pull out the like term, and you'll be left. Pulling out means you're dividing by it on the inside. So if I divide 3 by 3, I'm left with 1. If I did 3x squared by 3, like if I'm dividing each of these guys by 3, multiplying by 3, this becomes 1 and this becomes x squared. And we got the 3 out front. Now I can divide these to be 1. And so that's how you're left with 1 plus x squared divided by x squared. So these are the same. Simplify both fractions. So sorry to simplify them. Okay, well, how do I simplify them? This is one way. They're talking about prime factorization. So what they did is they said 12. Well, 12 is 4 times 3, and 4 is 2 times 2. So that's 2 squared times 3. And 42 is 2 times 21, and 21 is 7 times 3, so 2 times 3 times 7. And if you get it in terms of its prime factors, then you can easily cross out, and I'm left with 2 over 7. Same with 10. 10 is 5 times 2, 35 is 5 times 7. 5 divided by 5 is 1, so this is 2 sevenths. That is one way to show that these are equivalent fractions. That is not the only way. It says you write both with the same common denominator. So in this case, we found the lowest common multiple of 42 and 5, which is 210. And so then we're saying, oh, we multiplied by 5 here and here. We multiplied by 6. And then you can see that those 16 over 210, that those are equivalent fractions, with making them have the same denominator by multiplying. Another common thing is to multiply the two denominators together. So then you basically multiply each fraction by the other denominator. And that shows that they're equal. What else you could do, which I don't know why I didn't put that as an example. The easiest thing, in my opinion, is to just cross multiply, and if they're equal, then sides would be equal. So is 35 times 12 equal to 42 times 10? Well, this is 420. Is this 420? I don't know that by heart. So 6, 7, 5, 3, 0. So 420 equals 420. So to me, that's the easiest way to prove equal, is to just multiply. But those are some other ways And this is basically saying now they're equal if we cross multiply to get the same thing. A, B, C, D are integers. Then B is greater than 0, B is greater than 0, and A over B is greater than C over D. This is the same idea. We multiply across, that product on that side is bigger than the product on the other side. Given rational numbers A over B and C over B, there's another rational number between these two numbers. Okay, denseness is the idea that no matter where you are on a number line, you can get smaller because there's an infinite number of numbers. So even if you pick, is there a number between 1/3 and 1/2? Yeah, there is. So basically it's saying if you have two numbers, you can find another number between them. Two rational numbers, you can keep cutting the number line smaller and smaller and smaller and smaller and smaller and smaller because it is infinitely dense, right? These dots, there's dots in between the dots. Like numbers, there's an infinite number of numbers in between any given rational numbers. Find two fractions between these two because 1/2 equals 9/18. 8/18 or 4/9 is in between 7/18 and 1/2. So basically we turn them into 18ths. So we're like 1/2, if I multiply by 9, is 9/18. So if I put them on a number line, that's helpful if I have 7/18 and I have 9/18. Something in between them would be 8/18. So that's what that's showing. And then respectively, both greater denominators, it says I can make them into 36. So if I have 14/36, so I cut it into smaller pieces, right? In 18/36, you could put 15/36, you could put 16/36, you could pick 17s at 36. Any of those would be options. That's what they said right there. So this is saying if you add, oh, this inequality is going to be true. If I take A and add C, and take B and D, that A plus C over B plus D is going to be in between these two numbers. Okay, so that's a little bit about rational numbers, which rational, again, I think I forgot to say this. Sometimes people get confused by that expression. Rational has the word ratio in it. And the ratio is another name for a fraction. So that's what rational numbers are. So hopefully that helps. That's section 6.1. So stay tuned for 6.2.